So today we're going to get into chapter 17, and I have a demo today as well that we'll be going over. And so in chapter 17, we're talking about carboxylic acids and their derivatives. We've already talked a lot about carboxylic acids in a variety of ways. We've talked about how we can make carboxylic acids. We'll talk about those a little bit today to refresh our memories, coming back from spring break, right? So we will also learn a few other ways to make carboxylic acids and their derivatives, which are very important. Can anybody give me an example of a derivative of a carboxylic acid?
Alcohol.
Okay. An alcohol? That would be a product of reduction, yeah, but the carbon would still it would be a different oxidation state. So derivatives typically have the same oxidation state and retain the carbonyl. Acid chlorides. What else? What about your synthetic Snapdragon scent? What was that?
Ester.
An ester. Yeah. What else? Amide. Anything else? And hydrides. We'll be talking about those today as well. Okay. And there are also some other special amides and esters that we'll be talking about also. So, as you know, the carboxylic acid contains the carbonyl, right? The C double bond O, that's largely what's responsible for most of the chemistry that we're going to be talking about. And then there's some other electronegative atom attached here. If that's an OH, it's a carboxylic acid. If it's a OR, it's an ester, right? If it's a nitrogen, it's an amide, so on and so forth. So, esters, amides, how many types of amides can we have? Pardon? We can have three. We can have primary, secondary, and tertiary, and they're different by how do we distinguish them? You can distinguish them by the number of hydrogens or the number of carbons. That's right. So a primary amide would have two hydrogens or just one nitrogen carbon bond, right? So on and so forth. So all right, very good. Anhydrides are another type of carboxylic acid derivative. Okay? So what do you see here when you look at that? That's an anhydride. Where do you think the name comes from? Well, it can be symmetrical, but it doesn't have to be. Yeah, the anhydride functional group, the carbonyl, oxygen, carbonyl. That's the anhydride functional group. Where do you think the term anhydride comes from? Close. What else have we said that talked about that sounds like anhydride or anhydrous, right? Without water, yeah. So an carboxylic acid anhydride is really two carboxylic acids that have reacted with one another and spit out a molecule of water. Okay? And so you can actually make these from carboxylic acids. They are very useful molecules. Can anybody tell me what they're useful for? They're more friendly versions of acid chlorides, actually. Okay, so one carbonyl can act as an electrophile, and the other carboxylate part will function as a leaving group. Okay, they are more stable than acid chlorides, but they react and behave very similarly. So we can use anhydrides to do a variety of acyl substitution reactions that we've talked about in the past. Okay, they can be symmetrical or unsymmetrical. As you can see, the first one that you have there, the two R groups are the same. They're aromatic rings. That is a symmetrical anhydride. So the carboxylic acid that was responsible for this was just a single carboxylic acid. It was benzoic acid reacting with itself to make the anhydride. How about with the mixed anhydride? Why do we call it mixed as opposed to unsymmetrical? There are two different carboxylic acids that have to be in play to make that anhydride. Can you tell me what they are? Delaney's got a big grin on her face.
I feel so stupid because I have no nomenclature at all.
Don't feel stupid. Ethanoic acid, yes, which is also known as what? What's the more common name for it? Acetic acid, that's right. So this part on the right comes from acetic acid, right? Just concentrated vinegar. And what's the other carboxylic acid component? Benzoic acid, that's right. And you mix the two of them together with a catalyst that dehydrates the reaction mixture, and you can get the mixed anhydride, okay? You can also have cyclic anhydrides, okay, where the two carbonyls are actually tethered to one another through some sort of ring, in that case a 5-membered ring. Okay, that's a very common cyclic anhydride used in polymer chemistry, actually. Types of amides that we can have, we already talked about that. We can have primary, secondary, and tertiary, and as Matt correctly pointed out, we can look at either the number of hydrogens or the number of carbons. I prefer to look at the number of bonds to carbon, but whatever works well for you is perfectly fine. We can also have, excuse me, cyclic esters and cyclic amides, but they take on a special name when they're cyclic. A cyclic ester is known as a lactone, okay? It is known as a lactone, and you can have a whole variety of lactones. Here's a couple of examples. This is known as gamma lactone because you have alpha, beta, gamma carbons. It's a 5-membered ring, okay? So we can have a 5-membered ring lactone. We can have a 6-membered ring lactone, which is known as a delta lactone, okay? How do you suppose you could synthesize these in the laboratory? Remember there was a reaction that we talked about with MCPBA? It was a named reaction. Anybody remember what it was? We took a ketone to an ester. Well, you did an esterification, but you didn't make a lactone. You made synthetic snapdragon scent. What was the name of the reaction where we took a ketone and oxidized it to an ester using MCPBA? The Baehr-Villiger reaction, that's exactly right. So we could take the cyclic ketone, if we could get it, and we could do a Baehr-Villiger oxidation and get the lactone. Another way would be to take a carboxylic acid that has the right number of carbons in it and an alcohol down here at the end and do the Fischer esterification reaction that you all learned about and make the cyclic esters. They're all possible, at least on paper, okay? But one of the ways that lactones are made quite conveniently in the laboratory is by starting with the cyclic ketones that we can get fairly easily. The cyclic amides are known as lactams. The example here, we have two examples. The beta-lactam, because there's 2 carbons in the ring, it's a 4-membered ring, and the gamma-lactams, because it's a 5-membered ring. What do you know about beta-lactams just by looking at that structure? What would you predict? Ring strain. And so ring strain leads to what? Instability, which is more reactive or less reactive? Yeah, these things are very, very reactive. Many of you have come into contact with beta-lactams, probably, when you've gone to the doctor. Anybody know what they are? Anybody ever have a shot of antibiotics? Huh? Like penicillins? Penicillins are beta-lactams, and the beta-lactam is what's known as the pharmacophore. Anybody know what a pharmacophore is? It is that part of the structure that must remain for it to behave as a pharmaceutical, okay? And so all of the sillins, amoxicillin, blah, 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 the whole line, they are beta-lactam structures, okay? They're penicillin derivatives. Now, penicillin's a lot more complicated than just a beta-lactam. It's not the simple beta-lactam, but nonetheless, it is a beta-lactam that is responsible for the antibiotic properties of the penicillins. The gamma-lactams, do you suspect that those are more or less reactive than the beta-lactams? Much less. And in fact, If you tried to replace the beta-lactam of a penicillin with a gamma-lactam, you'd find that it has no activity. It has to be that beta-lactam structure, and it is that ring strain that's built into it that is responsible for the chemistry that we see. That is also the reason why antibiotics like penicillin have a shelf life. Quite frequently, if you go to the pharmacist, one of the things that they have to do is take the dry powder and reconstitute it, because these beta-lactams will rapidly react with water. Now, by rapidly, I mean over the course of several days. Okay, but for an amide, that's actually quite quick, because amides are typically unreactive towards water, or at least relatively unreactive towards water, right? And so you have to prepare these things fresh. The nitriles are also derivatives of carboxylic acids, although they look quite different. Why do they get thrown in the same category? What do you think, Katie? Why do they get thrown in the same category as carboxylic acids, the nitriles? What's common between the two? Pardon? What's common between a nitrile and a carboxylic acid? What guy? Okay. You got this? Okay, that's true. There is a polar bond. But there's a lot of things that have polar bonds that we wouldn't say are carboxylic acid derivatives, right? What do you think, Sam?
So the compounds have one carbon atom, 3 bonds to electron together.
That's exactly the answer. That's right. So now tell me a little bit more. What's the answer? Why is this and this in the same class? What you just read off the slide. What does that lead to in terms of that carbon? Well, it is reactive, but what else? Okay, there's partial positive, partial negative. But it turns out that the oxidation state of that nitrile carbon and the carboxylic acid carbonyl carbon are identical, right? So that carbon has an identical oxidation state as a carboxylic acid carbon of the carbonyl, so we throw them in the same class, okay? And it turns out that you can convert nitriles into carboxylic acids relatively readily, okay? So we all know that carboxylic acids, from their name, are acidic compounds, right? So if we take a carboxylic acid and we place it in water, we should set up an equilibrium between the non-ionized form of the acid and the ionized form. If you look at this, you would think that the equilibrium is equal, but which side of the equation does the equilibrium lie? For a typical carboxylic acid, where R is just a carbon group, would it lie to the right or would it lie to the left? What do you think, Matt?
I think the left.
You think the left. And why do you think the left?
Because you're not forming any anions.
Well, I'm forming an anion over here, right? The carboxylate anion. You're right. It does lie to the left. How do we know it lies to the left? Are they strong acids or are they weak acids? They are weak acids, right? Which means they don't ionize very readily, right? So it doesn't lie to the right. What's the typical approximate pKa range for a typical carboxylic acid? 6 isn't out of the question, but it's a little high. It's close. That's close to neutral. 16 is real basic, right? These are carboxylic acids, so we know they're going to be acidic. So the pKa has to be below what? 7. So give me kind of a rough range. 6 was close, but a little high. Yeah, 3.5 to 5-ish. That's typically where you're going to find a typical carboxylic acid, okay? And so the equilibrium, therefore, lies to the left because the pKa is not 0 or less, right? So we know that strong acids completely dissociate and form their ions, right, in water. And those pKa's are less than 0 or below, right? And so given the pKa information that we know or that we should have committed to memory, we can kind of predict which way the equilibrium lies. Now, it turns out that carboxylic acids, if the R group is fairly large, give me an idea of how many carbons there might be there to consider it fairly large. 5 or 6. Okay, let's go with 5 or 6. If you take something that has 6 carbons and a carboxylic acid and I place it in water, it's insoluble because it doesn't satisfy my 5-carbon rule, right? So for example, benzoic acid will just stare at you as you pour it into water. It forms little clumps. It doesn't go into solution, okay? However, we know that carboxylic acids will react with strong bases like sodium hydroxide to form the salt of the carboxylic acid. And these salts are more soluble or less soluble? More soluble, that's right, okay? And so we can actually use this procedure to isolate carboxylic acids from other mixtures. You all did this last semester. Remember when you took the separatory funnel and you had a mixture of a neutral component and an acidic component? You put them in a solution of, some organic solution, I forget what you used, maybe ether, right? And then you added some sodium hydroxide and you shook it up and the layers separated. And in the aqueous layer was your acid and in the organic layer was your neutral component. And you separated those layers. Then what did you do? To get your acid back, what did you do? That would take a lot of magnesium sulfate because you have a water layer, right? It's not just traces of water. We have a salt, right? And it's in the water. How can I get it out of the water without having to remove the water? Pardon? What would I react it with? Look up there. What would tell me, what would make it water insoluble? Add a proton, right? If I added a proton to the salt, I would get a water insoluble carboxylic acid. So how did you all get the neutral form of the acid back? What did you add to the water? What kind of acid? You added strong acid. You added something that had a pKa much less than the pKa of a carboxylic acid. If I recall, you all probably used sulfuric acid. And you added it dropwise until the pH was really low, and you probably saw a precipitate form during that process, right? And so you can use this process to separate carboxylic acids from other components. This process is actually used in natural products chemistry all the time. So you get a bunch of plant material that has maybe carboxylic acids and peptides and carbohydrates and all other kinds of things in it, and you want the carboxylic acids, you will extract them with sodium hydroxide because that will make them water soluble. The other material's not as water soluble. You can separate it through that process. Okay. We know that anything that stabilizes the anion of an acid makes the acid stronger, right? That's going back to 255. And so if we think about this, right, if we have the anion, which is a carboxylate anion, if I have an electron-withdrawing group that's attached to the carboxylic acid, is that going to make it more acidic or less acidic? It's going to make it more acidic, right, because it stabilizes the anion. The opposite is true if I have an electron-releasing group or something that donates electrons to the carboxylic acid, right? That's going to destabilize the anion because adding electrons to an anion is not a good thing. You want to remove the electrons and delocalize them, right? So we can stabilize or destabilize the anion and decrease the acidity. So we can have an entire range of pKa values for carboxylic acids depending on what's attached to the carbonyl. If we have an electron-releasing group, will the pKa be greater than or less than 3-ish? It'll be greater than. If we have an electron-withdrawing group, the pKa will be kind of less than the typical pKa range for a carboxylic acid, right? We don't have to do the math to figure it all out. We just need to know intuitively what these groups are doing and kind of how it's going to influence the direction of the pKa. So let's look at our good friend acetic acid. also known as ethanoic acid, as Matthew pointed out earlier, right? Vinegar. Vinegar has a pK of about 4.76, 4.75, depending on which literature you look at, okay? That's within our range of about 3 to 5 for a typical carboxylic acid. This is just a simple methyl group, CH3, right? And it has a pK of 4.76. Now, if I replace one of those hydrogens with a chlorine, is a chlorine an electron-donating group or an electron-withdrawing group by induction? It's an electron-withdrawing group because it's electronegative, right? Notice what happened to the pKa. What happened to the pKa, Delaney? It went lower, more acidic, by a little bit or a fair amount? That's kind of a lot because we're talking about a log scale, right? So, you know, if we say that, let's round the 4.76 up to about 4.86, that's 2 units almost, just under 2 units, right? A pKa difference. Now, if I replace another hydrogen with a chlorine, what happens? It goes down even more, becomes a stronger acid. And if I add a third chlorine, replace one of the last hydrogens with chlorine, now what do we have? We're getting close to the realm of a strong acid, aren't we? We're getting close to a pKa value of 0. So what's happening as we take these acids and we place them in water? What's happening to the equilibrium? Is it lying more to the right or more to the left as we go from left to right on that series of carboxylic acids? It is, that's right. I would expect the trichloroacetic acid to have more of the anionic form in solution than acetic acid, right? So we know that. We also know that this is what kind of effect? Is it resonance? It's inductive, right? So it falls off with distance, right? So since this is on the carbon directly attached to the carboxylic acid group, right, it has a big effect. But notice what happens as we start moving that chlorine further and further away. All of these acids are identical except for the location of the chlorine, right? So here, we put a chlorine right here. We have 2.85. Pretty darn close to what we see for this simple molecule, right? A little less, okay? But pretty close. Now, if I move that over 1, it goes back up by quite a bit, right? It's getting closer and closer to being like the unsubstituted carboxylic acid. And as I, get even further out. So what's that tell us? As we move the inductive groups further and further away from the carboxylic acid, the effect is less and less, right? It falls off quite rapidly with distance, okay? We also know that there are electron-withdrawing effects that can happen by resonance. And so if we look at some examples on these benzoic acids, benzoic acid has a pK of about 4.19. Where have you all used benzoic acid before? You probably know it as the sodium benzoate form. Anybody know what it's used in? It's used in food preservatives. So they take benzoic acid to make the sodium salt of it, and this is one of the components that they add to things like Kikkoman soy sauce as a preservative. It'll say on there, contains sodium benzoate. Okay? 4.19, kind of the pKa for that one. Now notice if we add electron-withdrawing groups like a chlorine or a nitro group, what's happening to the pKa? It's going down, meaning that we're becoming more acidic. And if we add a methyl group is an electron-donating group, right? Remember that from our chapter on when we were doing all the Friedel-Crafts chemistry? Notice the pKa goes up. So again, you can find electron-withdrawing groups will make the acid more acidic, and electron-releasing groups or electron-donating groups will make the acid less acidic. Okay? So let's talk about how we can make carboxylic acids. This first part, oxidation of alkenes, we've talked about before, right? We can take an alkene and we can chop it in half and get carboxylic acids. For example, if we take potassium permanganate hot, we will actually cleave the carbon-carbon double bond and get carboxylic acids. What happens if we do this reaction cold? If we take an alkene and we use potassium permanganate and sodium hydroxide and keep it cold, what do we get? We get diols, right? And how are they? Are they syn or anti? Syn. That's exactly right. But remember I told you that even though potassium permanganate is cheap, a lot of times we use other reagents like the osmium because this reaction has a habit of over-oxidizing. And so if it warms up, that diol that you form actually continues to react with the potassium permanganate to give carboxylic acids and chop that carbon-carbon double bond in half. And so you can get carboxylic acids that way. You can also do this by ozonolysis in the presence of peroxide. Okay? So if we take an alkene and we treat it with ozone, we get that ozonide, then that rearranges to the malozonide, which I told you weren't going to be responsible for. And then if we use something like zinc or dimethyl sulfide, we got aldehydes or ketones, right? But when you take an alkene like this and instead of using zinc or sulfur or dimethyl sulfide, you use an oxidizing agent like hydrogen peroxide, you'll actually get carboxylic acids as well. There's another reaction. This is known as the Tollens test, where you can take a aldehyde and you can oxidize it in the presence of what's known as Tollens reagent. We're going to do an example here in just a moment. You can get carboxylic acids. And you can also get carboxylic acids from primary alcohols by oxidation with what reagents? Jones reagents, right? Jones reagents will also oxidize primary alcohols and aldehydes into carboxylic acids, okay? And there are many, many other ways to make carboxylic acids, as we'll learn, right? But there are many, many things that you need to know about making carboxylic acids. They're very, very important functional group, and we have a lot of tools at our disposal to do it, okay? So I want to talk a little bit more about the Tollens test, and I've got a demo to do here in just a second. Does anybody know what this is? It is a sugar. It could be starch, but starch would actually be a polymer of this sugar. Okay, right, yeah. So we've got glucose up here, right? Notice what I've got an arrow pointing to. What is that? What's the functional group that that arrow is pointing to? It's not a carboxylic acid. We've got an OH and an OR. That's a hemiacetal. Okay? We talked about those a couple of chapters ago. Remember, you can take carbonyls and we can make acetals and we can make hydrates. Well, if you have a single OR and an OH, that's a hemiacetal. Okay? Not an acetal because we don't have two OR groups. But this sugar, when you place it in water, is actually in equilibrium with what we call the open form. What's the functional group now? For that carbon. Do we have a carboxylic acid yet? We have an aldehyde, that's right. So sugars, simple sugars like glucose, when you place them into water, they actually are in equilibrium with their chain open form, known as an aldehyde. So this aldehyde reacts with one of the alcohols, and it forms this hemiacetal. Now, one of your assignments for Wednesday is to tell me which alcohol reacts with the aldehyde to form the hemiacetal. Okay, so I want you to write that down on a note card and bring it to class on Wednesday. Okay, but when you have that hemiacetal form, it can react with Tollens reagent to give a carboxylic acid. Okay, or at least under the basic conditions of the reagent, you get a carboxylate. Okay, but you also get what? I'm going from silver. What's the oxidation state for silver in solution? +1. So it's a salt, right? What's the oxidation state here? 0. So it's what kind of silver? What kind of silver is silver 0? It's a solid. That's exactly. What do you know about silver? It's shiny. It forms a mirror, right? So what we're going to do is we're going to make a very expensive mirror here in doing this reaction. So this is known as a Tollens reaction, okay? And it allows us to make silver mirrors, basically, as well as carboxylic acid. So if you have a very expensive compact mirror, high quality, they are actually silver mirrors. It works better than just about anything we know of in terms of reflecting the image of your face back at you. Okay, works really, really well. And in the old days, this is actually how they made silver mirrors. Okay, so we're going to silver a flask, and we're going to start off by making some Tollens reagent. So I've got some silver nitrate. Okay, I've got some ammonia, and I've got some potassium hydroxide. You might want to move down more. So we're going to start off by taking about 20 mils or so, whatever I've got in here, of the silver nitrate. Does anybody know why I've got the silver nitrate wrapped up in black tape? Yeah, and why is that important? It will stain. So they used to, I don't know if they still do it or not, but when babies were born, they used to put silver nitrate in their eyes. I don't know if they still do that or not anymore, but, huh? They don't? So, it was an antimicrobial, yeah. Okay, so as you can see, clear solution. We're going to add a little ammonia. You might smell a little ammonia, don't worry. You'll be okay. You won't die. And we're going to add that ammonia. And are you seeing a precipitate form? Yeah, it's turning dark. And I'm going to continue to add ammonia until it goes colorless again. Hopefully that'll happen soon. There we are. We went back colorless. So we've just prepared a aqueous solution of silver nitrate and ammonia. Now we're going to add some potassium hydroxide. How much of that do I need? Let's see, about 12 mils. More or less. It's the nice thing about this chemistry, it doesn't have to be quite exact. And I'm going to add that to my silver solution. Now what happened? Yeah, it turned kind of muddy colored, right? And so that's not good. So I need to add some more ammonia, which is fine. This is how you make this stuff. And I'm going to add ammonia until it all goes into solution. There we go. Now we're back to a clear colorless solution. I'll just add a couple more drops just for good measure. Kind of like cooking. You add just enough salt and then just a little more, right? So what have I just made? I've made what's known as the Tollens reagent, which is an ammonium complex of silver, okay, in water. And I've got the hydroxide from the potassium hydroxide that I added. So this is the Tollens reagent, okay? And so I'm going to place this in this flask that we want to mirror. And now I'm going to add some dextrose. What's dextrose? Sugar. Yeah. It is a reducing sugar. How many of you have heard the term reducing sugar before? Huh? In cookbooks? No, you should have learned it in biology. Yeah, there are certain... We're going to add that. And you'll see that it's starting to turn colors on me.